Good evening, folks. This is stpete.net Meetup. I am John Calloway. That is Clayton Hunt. With us this evening, we have Steve Lorello. He's going to be talking about Intro to Computer Vision in .NET.
Hey, how are you?
We'll give it a few more minutes, let people wander in, make sure everybody gets a chance to grab some pizza, grab a drink, get comfortable. We'll leave the drop game on for a little while until presentation ready, and then we'll probably turn that off.
Yeah. So if it's Aaron all the way from Indiana because he left us.
Yeah. With that, who do we have from out of town? We are the stpete.net Meetup in St. Pete and Tampa Bay area, Florida. We know we have freaking Ward from Indiana. Are there others from other cities, other states, other countries even?
That would be cool.
Ward says, we're still here together.
Yeah, but where's my macaroni?
Yeah, Ward catered in barbecue for us at one of the meetups, and it was fantastic. And he brought a tray of macaroni for Clayton, and I think maybe a tray for everybody else.
That sounds good. That sounds delicious, actually.
It was good.
Quite good.
Like, like the big, huge trays like the like a foot by 2 feet or whatever. I ate nearly a whole one of those of his macaroni. It was awesome. I don't know how the rest of the food was, but I had a lot of macaroni.
I think I would have a rough day the day after that if I even attempted to do that.
It's all about the training. You got to build up to it.
You got to warm up for it.
Oh, we've got a new round to drop.
That round seemed to go faster than the last one. There we go. Oh, we bumped into... I didn't know we could bump.
We've got a Stark. We've got a Stark in the audience. Appreciate that.
Oh,
Clayton's dragging things across the screen.
You guys bumped into me. Ruined it for everybody. Oh, we don't control it. Just bang, drop, and then stuff happens.
Yeah, we'll give it a few more minutes and let everyone settle in, find a seat. Plenty of room up front. We've got Steve Lorello talking about Intro to Computer Vision in .NET this evening. Next month, we have Azure Bot Composer with Michael Stark. And in December, we have Design Pattern Mastery with Steve Smith. So be sure to follow us on Meetup, RSVP for all of the meetings there. You can follow us on Twitter. Of course, like and subscribe here on Twitch. And you can follow us on Facebook groups, as well as we do back up the presentations to YouTube as well.
Yes.
Yeah, I'm still trying to find the cheat codes for the drop game.
Is there
Doesn't seem to work. No, there's not.
You know? Oh, come on. Come on. I think I'm going to miss it. Oh, yes. Lowest score ever. I mean, next to nothing. I mean, I did get something, but... Wow. Flayshow is flying.
Nope, missed it.
Yep.
All right, we're about at 7:05, so we'll go ahead and start the presentation. Again, this is stpete.net Meetup from St. Petersburg, Tampa Bay area, Florida. I am John Calloway. Clayton Hunt is controlling all of the technology for us this week. This month, we have Steve Lorello talking about Intro to Computer Vision in .NET.
All right, cool. Let me just make sure my slides up.
Yep. And you are now presenting.
Awesome. So, hey everyone, my name is Steve Lorello. I'm the .NET Developer Advocate at Vonage, and I'm going to be presenting to you just a brief introduction in computer vision to using .NET. So of all the topics in computing, computer vision is probably my favorite. With it, you get to take a set of fairly abstract mathematical concepts and apply them to something that's really quite powerful, useful, and pretty neat. Now, if you're like me and you've ever dabbled in raw computer vision techniques before, you're probably like me. You've used mostly either Python or C++, and both are boundlessly useful, but honestly, like that is my favorite framework. So it's really neat for me to be able to kind of talk through these concepts and actually have examples with .NET. I'm really excited to actually start exploring this with you all. So a good place to start is by asking the question, what is computer vision? Now, to answer that, I'm going to borrow a quote from that my computer vision professor in grad school actually borrowed from another computer vision researcher. So the goal of computer vision is to write computer programs that interpret images. Now, there's two concepts that we're going to need to unpack here. First, what are we interpreting? And then maybe a little more fundamentally, what is an image? So here's a little bit of an agenda of what we're going to be covering in this talk. First, we're going to get into that existential question. What is an image? And specifically, what is a digital image? And then we're going to look at a little bit of basic code using OpenCV and .NET, just kind of showing you how to get up and running with it and even just look at an image. And then we're going to start diving into that interpreting part of our definition. We're going to be looking at convolution and edge detection. Next, we'll be looking at facial detection. And then we're going to explore doing facial detection in real time on multiple video strings, actually using Vonage's video API. And finally, we'll be doing some feature tracking and some image projection. So for our first question, what's an image? So here's an image of my muse for this presentation. He was my dog, Zero. Get used to him. You're going to be seeing him quite a bit throughout this talk. So what's an image? A digital image at its most foundational thought, insofar as CV is concerned, is a function. So that function denotes a quantized sample of intensity values along a two-dimensional grid. Those intensity values denote light intensity along arbitrary ranges. So for example, like we're talking about pixels here. So you might be talking the range of a byte, 0 to 255. And there's no rule that says that actually has to fall in that range, 0 to 255. That's just convention because it's the size of a byte. Oftentimes, when we're looking at grayscale images, those numbers are from -1 to 1 or 0 to 1. But technically, as long as they lie around any bounded range, the math still holds. Actually, when you get into other types of image processing, in particular things like high dynamic range, which is really popular today, HDR, the range of values that could express an image are much larger than 255, much larger than 1, or technically infinite. So the image of 0 we saw is a matrix of n by m. N by m, where n is the height and m is the width. And then there's 3 channels in there. Each channel denotes an intensity value for a particular color. So in the instance of that image that we were just looking at, the colors being represented are BGR, blue, green, red. So this picture here is an image of a pepper and is actually a classic example for looking at an image as a function. And specifically, we're looking at that image as a function in a one-dimensional space. Now, grayscale makes things a lot easier to think about, but the math actually abstracts to any number of channels. For example, the traditional RGB that you're probably used to, which just means red, green, blue. So take a look at the red line that's drawn through this pepper. You can think of that line, that single line, as its own image in one dimension. And that image if you look on the right here, is denoted by its light intensity values, with the darker spots having lower light intensity values and the lighter spots having greater light intensity values. And now this insight actually becomes really powerful. And we'll see later how it's applied, but I want you to think very briefly about something. Where are the edges in that one-dimensional image? Are they in the peaks of that graph? Are they in the valleys, or are they somewhere in between? So now we'll get into the crux of this talk. We're going to be talking about computer vision and .NET. In this talk, I'm going to be using a library, a couple of libraries, OpenCV, which stands for Open Source Computer Vision Library. As the name it suggests, it's an open source tool, and it's pretty widely adopted. There are other tools that do essentially the same thing as OpenCV. MATLAB, for example, Octave, for example. They both have a lot of image processing functionality. There's other things out there that do similar stuff. But I like OpenCV as, for the most part, it's free. The docs are pretty user-friendly, and they explain how to do everything. And as a bonus, they also explain all the math and insights surrounding what each function does. Now, Emgu CV is a .NET wrapper for the OpenCV libraries. And that's actually what we're going to be using to run this all in .NET and use this with .NET Framework and .NET Core. And there is, for the most part, a one-to-one mapping between OpenCV and Emgu CV. So most things that you can do with OpenCV, you can also accomplish with Emgu. So I'll note that if you're like me, I got my start with computer vision using the Python library, the Python OpenCV library. And you might need a little bit of time to adjust to Emgu CV because it's more closely tied, as you might imagine, to the original C++ implementation of OpenCV. And also note that if you want to use this commercially, Emgu does actually have a commercial license, but for open source stuff, it's free. To actually use OpenCV, just create a new project. I created a bunch of console applications to do this. They're all .NET Core console apps. And then you install the Emgu CV runtime package. And that's just emgu.cv.runtime.platform. So for my case, I'm running on Windows, so it's Windows. Now we're just going to add a little bit of really basic code here. So Emgu CV is structured around a bunch of static functions in the class CV invoke. Here we're going to use 3 of them. Note, I've already stored an image of 0.jpg under my resources directory. And that file is going to just be copied down into the build directory when I run. And so I'm just assuming it's going to be there. The first line reads that image of 0 into a matrix. As you're doing this, there's 2 things to note. First, the matrices that we're talking about are in the BGR space, the blue, green, red. I didn't misspeak before. It's not the traditional RGB space that you're used to. You can read them into the RGB space, but OpenCV just traditionally does it in the BGR space by default. All of these structures also implement the iDisposable pattern. So if you wanted to clean up the resources that it's using underneath, it's just as simple as using a using statement or just calling dispose explicitly. So the second line here creates a window of the name of the in the first argument with the matrix get passed in through the second argument. And then finally, this wait key function here, it's similar to gathering a console input. It just waits for you to press a key while you're focused on the image window. And without it, without this call, the image will disappear immediately and you won't get to see it. And so here it is, the result of our little program. We run as a console app. It creates a window and shows 0 lounging around the house. Hold on, I'll just kind of show you this running real quick before I move on. This is this basic, very basic app. Run it. And it popped up on my other screen, but here he is. There's 0. Cool. Pop back in here. So the next topic that we're going to cover is convolution. And convolution really starts to get pretty interesting. Convolution is the process of combining 2 functions together to produce a third. So when we're working with images, this generally means taking a large matrix, an image, and running a small matrix called a filter or a kernel over it to produce a third matrix called a feature image. And that feature image is actually where we're going to see a lot of our insights coming in. It's where stuff actually starts to get really neat. So this operation shown on this slide is essentially what's happening here. So the shaded region of the image is the same size as the kernel being run over it. The feature image is the size of the image minus half of the one dimension of the filter. So like even though it's 3x3 here, it would be, if this was instead of 5x5, 6x6, it would be 4x4. That makes sense. But essentially, this 3x3 submatrix's feature image is being, you derive that by taking the dot product of the filter or kernel with the image in these shaded regions, and you just run it over continuously. And from that, you actually get the output of this feature image. And that you just go 1, 2, 3, 4, 5, 6, 7, 8, 9, moving the feature window over it, or moving the filter window over it until you actually get a full feature image derived from it. And typically, when you're working with these, we like to normalize them back to essentially the original ranges. So you take the sum of this kernel and you divide that from the newly formed matrix, and that gets you your final product. So now that we've illustrated kind of what convolution is, I want to illustrate why it's such a powerful tool when we're thinking about computer vision. We can do some really neat things with it, and accomplish those things, we really only just need to tune the kernel that we're using. So this kernel right here that we're looking at is called a Sobel operator. The Sobel operator enables you to do something very critical, edge detection. I'll recall a few slides earlier when I asked you in that image of that pepper, where the edges are. Are they in the peaks? Are they in the valleys? Or are they in between of this graph? And the answer is actually in between. Now, if you took at some point, or maybe from a past life, you can remember taking calculus, you may remember something called a derivative. A derivative is just the rate of change of a function between 2 points in a function. It's a slope, essentially. And it's the derivatives that the Sobel operator is going to calculate for each pixel in the image. Remember how I said convolution is combining two functions or images to produce a third? Well, that's exactly what we're doing here. We're combining our input image and our kernel function to produce a third function, or a third image or feature image. That image is going to show the magnitudes of the derivatives, also more commonly known as gradients, and maybe more clearly thought of as the edges of the image. And now there's two Sobel operators that you need to use in order to derive this. And that's the Sobel operator in X, which is the one on the left here, G of X, and the Sobel operator in Y, which is G of Y on the right here. Now, after you calculate your gradients off of that, you can combine them to get a full gradient image, a full image of edges. So here he is again, 0, with his Mr. Rogers sweater, as I like to call it. Notice all the edges in that image. When you think about it, those edges, the places where the color is changing, is really where we're going to get most of the information from this image. The flat surfaces, the floor, the wall back here, even like this couch, the actual like couch surface, and even the white on 0, they don't really tell you much about the image. It's really in the contours and changes in colors that kind of tell you what's going on. So after running convolution with a Sobel operator over our image of 0, we're left with a gradient outline of the edges in the image. Those are the parts that are very bright. Now, the operation of convolution has a wide array of applications, particularly surrounding feature detection. And it's leveraged pretty commonly in something you might have heard of, a CNN, a convolutional neural network, which is a topic for a different day, but essentially it runs all sorts of these kernels over the input images and produces gradually smaller and smaller feature images that are then fed through a neural network and produce like predictions for something. If you want to calculate the Sobel gradients from an image, here's pretty much all you need. I'm assuming that I'm reading all these images in as color images. So the first thing I'm going to do here is I'm going to convert the input color image into a grayscale image. And that's what this first line is doing. CV invoke.convert color. It's taking the input image and it's storing the output in the gray image, and it's using BGR to gray. So it's just converting it between these two color spaces. The next line is something that you're going to see kind of a lot if you're working with image processing and computer vision, and that's a Gaussian blur. I'll explain what this does next, but it's actually blurring the image, which from our perspective is actually a really good thing, something that we really want. But essentially, we're taking that gray image, we're storing it back out in that same gray image, and we're running a Gaussian kernel over it, which I'll get to in a little bit, size 3x3. The CV invoke then .Sobel then, like, so these next two lines are actually what's going to calculate your gradients in X and Y. So this first one here calculates the gradient in X. You pass in the gray image, the output image that you want to store it in, and then the number type that you want to use to store the output image. So we're typically using BGR bytes. So like it's just the 3 channels stored as bytes, but now we're going to convert this and use very temporarily 16-bit shorts. And the reason we want to do that is when you think about that mathematical operation we were working on before, you can easily overflow the 255 boundary of a byte, in which case you're going to lose data from the image. So we just temporarily store it in this in these 16 bytes short or 16-bit shorts. The next two factors here are the 1 and the 0. The 1 is that's the factor at X that you're using. So by saying 1, you're explicitly telling it to calculate the Sobel gradients in X. The 0 is telling it to not calculate it in Y. And then the 3 here is the kernel size that you're going to use, the size of that feature image, or that, not the feature image, the size of that kernel or filter that you're going to run over the thing. And then it's the same thing with the gradient in Y, except we're passing in 0 for our Y and 1 for, or 0 for our X and 1 for our Y. The next thing we're going to do is we're going to convert the these grayscales back into the 8-bit space with this convert scale absolute value. So it's converting them back into that typical 8-byte space. And then finally, now, like at this point, we now actually have the gradients in X and Y. And then we finally need to actually combine them together. And to do that, we just do an add weighted. And we take the absolute gradient in X and absolute gradient in Y, and we put half a weight on either of them, and we store it in this Sobel gradient at the end here. And see here the gradient image in X and the gradient image in Y. Notice how they are pretty different from each other. The gradient image in X shows all the vertical lines pretty well, and the gradient image in Y shows all the horizontal lines. And this might sound a little contradictory, right? Because you think a Cartesian plane, X is horizontal and Y is vertical, but it actually makes perfect sense because when you're calculating the gradients in X, you're actually calculating the edges that are detectable in this direction. So the changes in pixel values as it's going this way, or as it's going horizontally. Therefore, you're actually getting the values that are perpendicular to the gradient that you're running against. And then the same thing with the gradients in Y. Since you're running up and down, you're just seeing the ones that are actually horizontal, that are perpendicular to the gradient that you're running in. And here it is again, our final result. Notice how you see both the horizontal and the vertical lines show up really nicely in this output image. So you can see both the vertical lines that we saw before and the horizontal lines. And it gives you a really good idea of what's going on in the image. And there's no color or really any other detail aside from the edges left in the image, and you really don't lose anything from it. So just quickly, I'm just going to pop out and I'm going to show this program. See, it's pretty much everything I just told you, except I'm declaring some stuff at the top. And I'm doing some in shows at the end. The in show is like the show thing I was talking about before. And I do some in writes too, so I can actually save the things as well. If I run that, I get the initial gray image is 0. And then I get the Sobel gradients in X image, Sobel gradients in Y, and then finally I get the combined Sobel from it. So yeah, that's pretty much how you do edge detection. Make it back over to this. So probably the most ubiquitously used kernel in computer vision is the Gaussian kernel. I touched on it a little briefly earlier. Lots of operations in computer vision will run what's called a Gaussian blur over an image prior to using it in other computer vision functions. For example, the Sobel operation we just saw. Gaussian probably sounds familiar to you. If you've ever taken statistics before or probabilities, it's just another way of saying a normal distribution or a bell-shaped curve. We start with some central mean value. That's the peak up here. And then as you get further and further away, the frequency kind of falls off. And similarly, we start with a center value, which is the weight that we're giving that pixel in the filter. And as it falls away, the weight of that pixel goes down. So as it gets further and further from the central pixel, it falls down and it loses weight. So that actually enables you to do this kind of blurring operations. And one of the things that really confused me when I first started learning about computer vision is, why is blurring useful? I mean, blurring makes it harder for us to see what's going on in the image, right? So why would it be useful for our algorithms? And the reason it's useful is actually because digital camera sensors, and film for that matter, they tend to actually add noise to the images. And even a little bit of noise can really throw off a lot of these techniques. Blurring images, pulling in different parts of the neighborhood of pixels around the image, actually mitigates those issues when you're dealing with digital camera images and actually regular film images as well, for that matter. But it actually allows the algorithms that we're using to more smoothly go over the images. So blurring digital images, which make it a little less detailed to our eyes, actually enhances these algorithms' ability to perceive and understand these images. So just to illustrate to you real quick why Gaussian kernels and blurring are so important, take a look at these two images right here. That's the image of our pepper from earlier, and of course an image of Einstein with some, and both of them have some artificially added what's called salt and pepper noise. Now, that noise is really obvious to us, whereas a noise straight off of a film or sensor may not be immediately obvious, but it does exist. And now think about the edge, that edge detector we were just working with, right? How is that going to operate? I mean, it's detecting changes in pixel values between pixels in an image. And as you can see, the pixels in here are sort of corrupted between different pixel values. So it's going to work pretty poorly, you might imagine. So while this detail, even though the detail in here is still perceivable to our eyes, to that algorithm, it's still not going to be able to see it. It's not going to be able to see the oscillation of those pixels. So it's really kind of important to blur your images, what it comes down to. And another cool function that you can do with convolution is you can do sharpening. So a sharpening filter kind of works conversely to a Gaussian filter, a blurring filter. Makes sense, right? But instead of weighting some of the pixels around your neighborhood of pixels against the center pixel, it's actually upweighting the center pixel and enhancing the detail that you get from it. And you can actually do this in two ways. You can either use the sharpening filter, or you can take the blurred image and subtract it from the input image to get a detail image, and then add back the detail to the original image to enhance the detail in that image. And so this next bit right here, we've actually taken our image, we've run a Gaussian blur on it. And like we saw in our last code snippet, we can actually, just like we saw in our last code snippet, and now we can actually create a detail image by subtracting that blurred image from the input image, and then by multiplying it by some factors. So for in this case, I multiplied it by 2. And then we can calculate a sharpened image, which is taking the input image and then adding that detail image to it. And so see here, now we're going from our original to our blurred image. And now the one on the left here is the difference between the original image and the blurred image. So that's the detail image. And if you add that back to the original image, you get this sharpened image. And it's actually probably easier when you're comparing apples to apples. So see here, we have the original versus the sharpened image, 0. You can see the differences in sharpness here. And you can actually tune the degree to which you're sharpening an image by changing the multiplier that you're using to increase the sharpness. But I would advise you not to overdo it, as if you do, it can actually wash out the image and you get some weird artifacts added. See here, this one's actually done that same function, except instead of adding 2x detail, we've added 10x detail. And as you can see, a lot of the pixels start to wash out, like tons of the pixels do, actually. So now, actually, let me just show you that real quick before I move on to the next section here. Can I hit the escape button again, which I shouldn't have, but it's okay. Same deal. So that's the original image and blurred and the detail. And finally, the sharpened image. All right. So cool. So now we're going to move on to something else that's really neat, and that's actually face detection. And using OpenCV, we can actually run face detection in real time on multiple video streams, with low overhead, actually. So we're going to be discussing a technique for facial detection developed by Paul Viola and Michael Jones. And it's both really robust and really fast. So we'll take these little masks called Haar-Like features, which we'll see in a minute are just these very simple little shapes. And with them and an integral image generated from our input image, will determine the relative shading of the different regions of the image. And after combining a lot of these Haar-Like features together, we can build what's called a cascading classifier to perform facial detection. So these Haar-Like features, as they're called, are simply black and white images split into 2, 3, or 4 different rectangles. They may look like silly little shapes, but they're actually extremely useful tools for all sorts of detection algorithms. In this case, we're going to be using them exclusively for facial detection. Now, 1 or 2 of them by themselves aren't particularly useful, but hundreds of them applied at varying scales against the same image using a well-tuned model produces a very robust and, more importantly, really, really fast result. And I mean, it can run in real time on multiple video streams with low overhead fast. But wait, you might be asking yourself, you're running hundreds or thousands of these at the same time. You have to set them up and subtract all of the pixels under each region at varying scales. How could that possibly work and possibly work performantly? And the answer is at the core of the Viola-Jones algorithm, and that is an integral image. So the integral image, we thought we were done with our calculus terms. The integral image, as you might recall, what an integral is simply the area under the curve. And that's exactly what these are when you're thinking about these images as functions. The integral image represents the sum of every pixel above and to the left of every other pixel in the image. So what does that do for us, you might ask? Well, the Haar-Like features are only occupying a certain neighborhood of these images, and it makes the summations of those Haar-Like features, the black portion and the white portion, very fast. So typically, if we were running this without an integral image, the summations, so each of those summations would be of order n by m, where n is the height and m is the width of the feature. And this might be acceptable for one feature, but this algorithm requires us to run lots of them over the same feature image or over the same image to detect faces robustly. So this diagram actually illustrates how the integral image makes the algorithm move so much faster. So to find this red rectangle, which could represent one of our Haar-Like features, we only need to take the bottom right corner of our integral image, subtract the bottom left corner, the top left corner, and then add back the top right corner, and then add back the top left corner. And that's it. Remember, we've summed everything up and to the left of each pixel in this image. So D is this whole rectangle here. C, which we're subtracting, is this rectangle. B, which we're also subtracting, is this rectangle. And A, which is this portion up here, this little region, which got double negated when we subtracted B and C. So you take all that, you add it, and you take this like simple little equation down here, and you've got it. So with these, we can run really quickly the shading of the regions covered by our Haar-Like features. And with some other machine learning techniques, we can correlate them all together to build a classifier that will swiftly and robustly detect faces in an image. So how does this apply to our .NET program? Well, it's actually quite a bit easier even than I just described. OpenCV actually has a large collection of Haar-Like features prearranged into a model for a cascading classifier. That model is just available in an XML file that can be easily integrated into using Emgu. With that model ingested, we can construct a cascading classifier. And then it's just as easy as running, I think it's detect at multi-scale method, or I think it's just actually a detect method. And then drawing rectangles around the faces that we've detected. And here it is. This is all you need to do to detect a face in .NET. You need to build your classifier. So this is this new classifier from this XML file that I referred to earlier. Then you need to pull in whatever image that you're looking at. So read the image. Then you just need to detect the faces at multi-scale. That was right. It was multi-scale. So detect faces at multi-scale. You pass in the image. I pass in a min size, and I will tell you why in a moment when I'm actually showing the result of this off. And then for each image or for each face that it detects, it's just detecting a rectangle. I just call the CV invoke that rectangle on that image and draw the face with a blue line with blue lines. And that's pretty much it. That's all you have to do. And so here's a result when run against an image of me. As you can see, it detected my face. So now the reason like I said earlier, the reason I had to add this size in here was because this algorithm is actually, it doesn't care that much about the scale of a face in an image. And without that 300 by 300 constraint in here, it was actually picking up that the face of Roger Clemens on a bobblehead back there. which wouldn't look right. So I told it to clamp down to 300 by 300. Now it's like I said, it's invariant to scale. It is not invariant to lighting changes. So anything that would change the relative shading of like one half of your face could throw it off. And also it's not invariant to rotation. So if I rotated my face, if I didn't have a specific classifier to detect like the profile of my face, it wouldn't work. So now we're going to be looking at the same technique, but applied in real time, in a real-time application to see just how powerful it is. So I'm going to be doing this with the Vonage Video API. So I'll be building just a video call app that will detect faces in real time on both streams that are in the call. So I'm just going to build this as a basic WPF client app. I'm going to add the OpenTalk.client SDK to it, and a new class implementing a special class from that SDK called iVideo Renderer, and that's going to be called it's going to implement that interface. And I'm going to call it Face Detection Video Renderer, and it's also going to extend a control because it's going to be a control that we're putting in our WPF app. Then we're going to add one of these to our main XAML file at the lower left-hand corner, lower right-hand corner of the layout. And that's going to be where the publisher's video, my video, is going to go. And also we're going to add buttons to connect to the call and detect faces, and we'll use that later. So now that we have the main window set up, in the main XAML CS, I'm going to construct a publisher and a session. Ahead of time, I've gone ahead and built an API key. I got my API key from my account, my session ID I generated, but you can generate that dynamically. And token, you could also generate that dynamically using our stuff. So that's all been created dynamically. That could all be created dynamically, but I just hard-coded in here for simplicity. Notice how I'm constructing publisher here. I'm passing in the publisher video, which is that face detection video render that I referred to earlier. That's going to have the ability to capture each frame as it comes in, run a detection on it, and display it. So next, when we need to manage our connecting to a call, when the user presses the connect button, we're going to flip between the connection state of the session. So just a simple connect and disconnect. And we're also going to unpublish on a disconnect. The next step is when someone pushes the detect faces button, we will, for lack of a better term, start detecting faces. So we'll toggle the publisher's video, and then any subscriber videos that we have, we'll also start detecting faces on them. Now, this function right here, we're going to register to the on-stream created event callback. So on-stream created is when someone joins a call with a video stream. And with that, we'll just create a new face detection video renderer. And we'll add that to our grid and turn the faces on or off appropriately for the rest of the session. And then, of course, we'll subscribe to it. So now that we have the layout and session initialization working, we need to manage the actual real-time face detection and the displaying of those little rectangular boxes. So by having the face detection video renderer implement the iVideo renderer, we're going to be getting each frame that comes through that renderer. We're going to intercept each frame and run facial detection on it, and then we're going to draw a rectangle on each frame to show where the face is, or faces are, and finally render the frame. So here's the beginning of our render frame function. Now, render frame is an implemented part of our iVideo render interface, and it's going to be called each time the renderer gets new frames. Each time either the publisher pushes out a new frame or the subscriber sends in a new frame, we're going to call it. So we're going to create a writable bitmap, and that's what we're going to be doing our face detection on, and it's also what we're going to be doing our drawing on, and it's actually what's going to end up rendering the image to the users when it's done. So I'm just going to obviously set the background to the image source of the background to this video bitmap. Next, we need to marshal the buffer from the frame into an image. So if we're detecting faces, we do just that. The image is constructed as a BGR byte image. Remember that blue, green, red, and byte. So that's the size, the 8 bits. And then we're marshaling that from the frame's height, width, and the actual buffer itself. And then I have some other control code in here, just in case I needed to like throttle this back. I actually didn't at the meeting to, but like if it's greater than a particular time interval, in a real-time video, you're looking at 30 frames per second usually when you're doing a video call. So that's approximately 33 milliseconds. I figured if worst case, I could just have this set like 100 milliseconds or 200 milliseconds if it didn't run performantly, but it did, and it actually works really well. But I actually do, to make this more performant, what I actually found was reducing the size of the image made a sense. Like I said earlier, this technique is invariant to scale. So by running it through this resize function and actually reducing the size of the image, you don't lose anything from the algorithm's performance perspective. Maybe you lose just a tiny bit if you're losing detail in the image, but for the most part, it works exactly the same and it runs much faster. So I dropped it by the size by a quarter, and the speed at which it ran, I think, dropped from 100 to 150 milliseconds per frame to 10 milliseconds per frame. So, like I said, when you're talking about like a 30 FPS video, real time is 33 milliseconds between frames. So it's actually running in real time. Now, after that, I add it to a concurrent stack of images, and you'll see in a second that there's a thread that's perpetually running in the background, running face detection. And it adds that to that stack of images. And after that's done, it'll actually go through, and any faces that have been detected, it'll just draw on the bitmap, and then it'll actually render the frame. So meanwhile, this bit of code is spinning in the background. This is actually where the faces are being detected. Notice how we start this in a thread pool. That way, when we want this operation, we want this operation to run on a different thread, because this operation actually has to run on the main thread because it's doing rendering. If you remember, like WPF, you can't run any rendering operation off the main thread, but we don't want to block that. So we're doing this on background thread, so all the working tasks are happening on this background thread here. And so we're running this on this different thread. We're popping these images off the stack, and then we're running our facial detection on them, and we're setting the faces for this face detection video renderer to whatever we've detected. And so then if someone comes in and they want to cancel it, we have a operation cancellation token that we're passing in, and we just cancel the operation. It pops out of here, and it shuts down the thread. Now, the reason we use a stack and I'm using a stack and not a queue in this case is because both the most relevant and last received frame are one and the same. And I do actually, this is just kind of a trimmed down version. In the full version, I actually have this checking to make sure that it's not backing up. If it is, just dumping the old images out of the stack so it doesn't get too backed up and do some weird things. So now that we detect faces, now that we've actually detected faces, we're going to drop into this last function here. That's this last part right here. And we're actually going to draw the rectangles on the bitmap. Note we need to scale back up the X and Y coordinates as we scale down the images. And also, interestingly, the OpenCV rectangle function that I used in the other app, or the other little console app I showed you before, didn't play nicely with WPF or these video frames for some reason. It actually corrupted the images. So I had to find another application online, or an extension library online that actually did this. And weirdly, this library rendered the x coordinates in points and the y coordinates in pixels, and which is why I have this pixel point conversion right here, multiplying it. But after that's done, we just draw 4 lines in the image and we're good to go. That's pretty much it. So I'll show you that real quick. But you know what? I'm going to need to shut down my camera. 1 second. Yeah, because it's not going to show me anything. I will be right back. Still here. Just can't see me. See, that's Windows for you. It's very possessive of your camera. So here's my application. So now if I run detect faces on here, as you can see, it detects my face pretty easily. And now I actually have another instance of myself on my other computer that's been on another video call with me this whole time. And I'm going to turn that on and see if that works too. And there I am. Hey, cool. So yeah, as you can see, it actually runs pretty well on both streams at the same time. And like I said, it's not that good at detecting faces in profile, but there are actually separate models that will do the detection of your face in profile. And yeah, I mean, actually it's doing a fair job. Yeah, it's doing a pretty good. And I was detecting my hand. There we go. It's actually not doing terrible. But yeah, so that's that application. It's pretty neat though. It's pretty well. And like I said, it runs pretty much in real time. When we're talking about video, like a video call, you're usually talking, like I said, 30 FPS in your best case. And that's running in, like I said, I think 5 to 10 milliseconds per frame, which is, real time. And that's chugging along there. Now, for our last bit of this talk, we're going to be covering some important concepts that lead to the basis of all sorts of things. And it leads to the basis of all sorts of things, from like augmented reality all the way up to panoramas. And that's feature detection, tracking, and image projection. You know what?
Real quick, we have a question in chat.
Oh, go ahead.
Freaking Words asking, are you able to apply multiple detection strategies at a time?
Multiple detection strategies at a time, like essentially, could I run it on my eyes and my profile and other things? Yeah, sure you could. You just have to the classifier only supports like one model at a time. So I would just have to generate multiple classifiers, and I feed that its own model, and then basically it would perform. You would just run them all successively, and you get whatever detection things you want from it. Now that could affect the performance of it, right? So if you have to run 5 millisecond operations once per frame, that's one thing. But if you have to run it 6 times per frame, maybe you want to throttle it back a little bit and tell it to only run it on like the 10th frame or something like that. That way you're updating everything 3 times a second, but you're not like killing your computer at the same time. So anyway, I guess, hold on, I don't even have Twitch up. Let me see and answer his question.
Yeah, would it be applying multiple classifiers or multiple models at that point?
Multiple models. Okay, multiple detection strategies at the front. Yeah. So in that case, it would be multiple models, multiple classifiers. But yeah, so in the resources section at the end of this talk, I actually link to this GitHub page. I think it has the source material for where I pulled that XML file from, and that actually has like profiles and eyes and all sorts of things. All right, cool. So I'm going to move on to this last topic here, and that's like I said, feature detection, tracking, and image projection. So the first question that we want to ask here is, what makes a good feature? So a feature is, I probably should update the slide because it should go back a little bit. What is a feature? So what we're looking at here is essentially correlating two images that are of the same scene, but they have, they're taken maybe at slightly different perspectives, or the scene looks just a little bit different. And the features are the things in that scene, the little individual points in that scene that will allow us to correlate the two images together and actually draw a correlation between them. So the first question I now ask in my slides is, what defines a good feature? And this is something that's not subjective. We really need a concrete definition for our algorithms to understand what they're going to be looking for. So I'll talk about that in a second. Then we're going to be using a object brief. I forgot what ORB stands for, but we're going to be using an ORB detection method. I think it's on my next slide what it stands for detecting features in an image. And then we'll be pulling the descriptors that gives us. And we'll be I'll just show you very quickly how to track images or track features between images. And then all of that kind of combined together leads to actually projecting images onto each other.
And real quick, questions in chat. Have you tried running any of this on IoT devices or such as Raspberry Pi? Do you know if any of this would run in Xamarin Forms, Android, iOS, or UWP?
Yeah, so that's actually a really good question. So I know that Emgu has a Xamarin Forms library or a Xamarin library. I've not tried it in Xamarin. And as for IoT devices, I don't think I've ever seen this apply. I don't think I've ever seen MguCV and .NET applied to an IoT device, but there's certainly, I actually know people from Vonage who I believe have done IoT integrations with OpenCV. There's a blog post I can find. It's like person detection with OpenCV, and I'm pretty sure they use an IoT device and a Raspberry Pi in that blog post. It was written on the Vonage blog if you want to look for it. But yeah, before I keep going, does anybody else have any questions? I guess. Yeah, for sure. It's definitely possible. Yep. All right, cool. I think I'm just going to keep going, then keep rolling. So we'll be taking those descriptors, like I said, and correlating the features gathered between images. And this will eventually lend itself to image projection. So back to that first question, what is a good feature? So a good feature is a section of an image that has multiple edges running through it. Now, why is that? Well, think about it. If you're trying to compare two images to each other and you are only looking at a very small portion of the image, if that portion doesn't have any edges at all, how are you going to correlate it to anywhere else in the image that is of the same color? You're not going to be able to. If it only has one edge, I mean, you kind of have a sense as to where it is, but like, if you look at this edge right here, this edge could correlate to anywhere on this slide, right on the side right here. So again, I mean, it's not good for correlating different parts of that same image. But if you have multiple edges running through the same point, the same feature, that actually enables you to say, hey, I can see these two edges here, and if I look a little bit to the left, I can still see those same two edges there. And so that makes them really good features. And they're actually called corners, typically, like features one name, corners is another. And we can see these really quickly with these. This is what it is: oriented fast and rotated brief method called ORB. And like we can do corner detection really easily with that. So this bit of code right here actually does feature detection on one image. It generates an ORB detector and calls detect and compute on it. So news up an orb detector says, I want 10,000 features. And then it calls the text and compute on it, on the image, stores the features and descriptors out in output matrices. And then the features 2D toolkit is a library that Emgu has to actually do some cool stuff with features and just draws the key points, the detected features onto the image. And as you can see here, the features that are being highlighted are kind of where multiple edges are coming together in this image of me. And when you're trying to correlate these between images, it makes it much easier when you have these kind of edges being detected. Or not the edges, I'm sorry, features being detected. So the next thing we'll think about here is, now that we've detected some features, is to do a feature match. And we're going to use a k-nearest neighbor matching function in the brute force matcher in MGU-CV for this, just to make it very simple. But like, there's multiple feature matchers that you can use. Brute force is the simplest. I can't remember any of the other ones off the top of my head, but anyway, essentially we're running that same detect and compute on two images, and we take the descriptors from the first one, add it to the brute force matcher, and then run a k-n match, passing in the descriptors in the second one. And then we're going to take the output of these k-n matches, and if they're within a certain distance of the other matches or the key points, like it calculates a score basically that it's looking at to determine if it's close or not. And the lower the score, the better the feature. And it will actually it'll correlate then the features together, and then it will draw the matches between these features in the output. And so here's two images of me with this done. And it's actually, as you can see, there's a couple of weird spurious ones like this one and this one. But when you're playing to the aggregate, this is actually correlating these two images very well. So now the last topic I'm going to cover in this talk is image projection. And to do image projection over multiple frames of an image of the same scene, we need to keep track of features between images and build these translation matrices called homographies to map the old pixels onto the new ones. The system of equations that this sets up, that's set up for these by these changes in perspective, have 8 degrees of freedom, which means that we need to at least match 4 features in an image to compute an appropriate homography to project one image onto another. So like, for example, we have, probably scores in this one, maybe even 100. We only really need 4 technically to get this to work, to actually correlate 2 images together. So now think about all the things that you can do with a 2-dimensional image. You can move it around, which is called a translation. You can rotate it. You can change its scale, make it smaller or bigger. And you could do like a perspective warp on it, where you look at it maybe from a different perspective, and the way it's shaped changes in your field of view. And these changes in an image can be generalized into this system of equations right here. And don't worry, you don't actually have to know any of this, but this is essentially the math that kind of sets up this homography down here. And this system of equations allows you to use this homography here. This is like, you don't have to compute this again, Emgu will do this for you. But that's actually the translation between one image and another, if you're moving between the 2 image spaces. And so this last bit of code here is just a really, a very simple example about image projection. It takes an image of a cat face, and it will scale it down and put it in the appropriate place in an image of my face. and then it will project the cat image onto my face using homography. Now, remember how I said we need at least 4 points? Well, we've got 4 points. We've got the corners of my face that were detected, and our cat image, that the actual 4 corners of the cat image. We calculate the homography using find homography between the two sets of points, and then we do a perspective warp to warp the cat image into the same image space as the image of my face, and then we finally copy that projected image onto my face. And here you have it here, my face replaced by a cat face. It's a little bit crude, but you kind of get the point. Now, if I wanted to project this onto running video, for example, I could do that as well. I just need to keep track of the image space I want to project onto and update the homography appropriately to project onto it. So I really hope that you enjoy this little stroll down computer vision way. It's a really big field, and we've really only nudged the very tip of the iceberg of its potential. There's a lot happening in it. Before you go, I just want to tell you a little bit more about me. Again, I'm Steve. I've been a developer for about 6 or 7 years now. I consider myself really a .NET developer first, and I'm the .NET developer advocate for Vonage. I got my start working on the global positioning system, better known as GPS, and I've also worked on the air traffic control system in the United States and the UK. I did all that prior to moving into advocacy. My nights and weekends, I actually study computer perception and robotics at Georgia Tech. Go Yellow Jackets. I'm also a graduate assistant there. You can follow my blog on Dev2 or my website, slorello.com, and you'll notice a theme to it. I like to take the Vonage APIs and like all sorts of computer vision and AI stuff and integrating them all together with .NET. And you can follow me on Twitter at slorello. And also, before I go, I guess I'll just tell you a little bit more about Vonage. We're not just the funny internet phone company anymore. We also have we're mostly enterprise communications now. We have a full suite of communication APIs, from text messaging to phone calls to obviously video calls like we just saw. You do SIP trunking, all sorts of things. And we have a coupon code here if you want to check us out. So here's the resources from this talk. So it is in there, like pretty much everything, all the examples I just walked through are all available on GitHub. Now, like I said, I've always found the OpenCV documentation really cool. Like I said, it kind of explains not only how to do things, but also the math and the reasoning behind kind of everything that you're doing. And if you're interested in computer vision, I definitely recommend giving them a read. Now, before I go, does anybody have any questions? So, anything else from Twitch?
Yeah, we've got a question in chat. How computationally intense is the video image projection?
It depends on how well you optimize it. I will tell you, in my experience with OpenCV, it runs about 10 frames per second. Now, obviously, you have things like Zoom has its background thing, which I think is also probably image projection, and that runs quite a bit faster. But they probably have a team that has more time to work on it than I do. Do I find the Emgu CV library as performant as the Python and C++ libraries? I haven't seen a difference in performance. It is really just truly a wrapper around the C++ library. So I guess any loss in performance would be marshalling between the CLR and the native space, but I haven't really seen any performance differences.
Yeah, and seeing a lot of the examples that your images of your dog and how you modified the image through code. I do a very little bit of image manipulation, usually weekly. When we publish the podcast, we'll put together a little thumbnail image or something like that. So I use something like GIMP for Windows or Photoshop or something like that. So playing around with some of the blurring, some of the image sharpness, some of the unsharp mask, so I can get a better sense of how they accomplish that.
Yeah, like these concepts are a lot of what's kind of applied in like Photoshop and GIMP. They like Photoshop in particular, Adobe has engineers that are paid a lot of money to build this stuff. So like, they basically take a lot of these same concepts and apply them to Photoshop, but at a more truly professional level than I'm giving you, because it's not my day job, right?
Yep. Any more questions, anybody?
So is there... Oh, can you reshare so that Clayton doesn't have to putz around with the images?
I'm sorry.
It's fine.
Like he was like, I didn't see him sharing anymore. I apologize.
No problem.
Well, it's the cameras are tied.
Oh no, I'm so sorry.
That's fine.
No problem. So it sounds like if you really want that high speed, quick functioning, high level performance, you're going to do something in C or C++, probably. Is this?
Yeah, probably still.
Okay. But the fact that there are these layers of abstraction or other libraries that do the things that make it a little bit more accessible to those of us that are still working in different languages.
Yeah, I mean, it's nice to see it in like in C# for sure. It makes it easier for me to interpret. Obviously, I can read Python. I can do all the slicing and dicing that you do in Python, but it's still nice to see it. What was I to say? But yeah, I mean, like when you think about it, like a lot of video technology is still in C and C++. Like even like Google Meet or is essentially running on top of browser APIs that are all running in C, right?
Excellent. So what's next for you? Are you doing more presentations in and around the country, or?
I have another. I'm giving a talk next Monday, I think, to a group in the UK. Obviously, I'm going to be sharing from home again, and then I have another talk at the end of the month. I'm giving at Prague, which is this same talk, and then the one next week though is actually on Blazor, which has been a lot of fun to play with, honestly.
I love Blazor.
It's really neat, isn't it? I was just talking to a colleague of mine at work. We were talking about Blazor, and like he hasn't really touched it yet, but I have, and I've done a look. Like I haven't gotten to build any production workloads on Blazor. So I'm a developer advocate, so we don't necessarily build production code anymore. We just build like proof of concepts and cool little demos. But I mean, the ease of use by comparison to like even stuff like MVC is like really cool. It's just like, oh, that's so much easier to do than what's in MVC.
Yeah, you can learn to develop. You can learn what you need to learn to develop most kind of line of business application stuff in like an hour or two, and then you're off to the races.
Yeah. I mean, it's really nice to see, and it's nice to see that it's not going like it doesn't seem to be going the way of Silverlight.
No, it's on the newest, supported by every browser technology. So they're not going to be able to get rid of it that easy.
It's great. I mean, like I was skeptical about Blazor Server, but that seems to be working pretty well. I still don't know if I would use that for like something if you have tons of clients using it at the same time. But yeah, Blazor WebAssembly has been really cool. And honestly, like, I don't know how much you use SignalR, but SignalR and Blazor WebAssembly is just so well integrated. It's incredible.
The only SignalR I've used is Blazor. So
yeah.
And you don't see it. It's just kind of works.
I don't mean like the SignalR, the WebSockets between the server and the browser.
Or like actually using the hubs.
Yeah, actually using hubs and stuff.
Yeah, no, I haven't messed with it.
Yeah, so like in when you're talking like the old SignalR, like 5 or 6 years ago when it first came out, I remember we had like we had a guy at work whose only job was to make sure all the hubs kind of worked and all the SignalR played nicely, and it was and it's really cool to see it just progress so well, and it's just so tightly integrated now. It's nice.
Mm-hmm.
Well, we can hang out and continue chatting, but I wanted to spam chat with a bunch of links to Steve's blog on dev.to, Twitter account, links to all of the stpete.net meetup stuff. Of course, we very much appreciate Steve taking the time and speaking with us today and sharing. Join us next month on Tuesday, November 10th with Michael Stark. He's going to be sharing about Azure Bot Composer. And then in December 8th, we have Steve Smith talking about design pattern mastery. So here comes a flurry of links, and Steve, feel free to add more as well.
Yeah, and SC Farmer did have a question about what you've used SignalR for as far as work goes. I don't know
hold on.
But...
Yeah, sure. So like, so Vonage, for example, enables you to build applications that like send and receive text messages, WhatsApp, Viber, Facebook Messenger messages, stuff like that. You can make phone calls. I just actually had a blog post come out today where I ran an inbound phone call through an Azure translator and then piped the output from that back out to a web browser. And the WebSocket coming in from Vonage is not a SignalR. The WebSocket going up to Azure is not SignalR. But once it comes back into the application, it has to go back, get shipped back out to the browser. That's actually going over a SignalR hub out to the client application. I'll actually just drop a link to that real quick. Here, it just came out today. And it's using Blazor WebAssembly. But yeah, I mean, like, so like a lot of the stuff is like, you know, like webhooks and stuff like that, and actually getting to see that come into your browser is really neat, like through like a .NET application. And like I said, with Blazor, it's not, there's no question as to what the type is, and there's no weirdness surrounding like getting stuff to work. It just kind of works, which is really nice.
Yeah, I've abandoned all the JavaScript frameworks pretty much, switched straight over to Blazor.
Yeah, you know, I was just starting to ramp up again on Angular when I started working with, when I started looking at Blazor. I'm like, oh, I don't want to do anything else anymore. I'm done.
Yeah, we've our main application where I work is a Angular 2+ application.
Yeah,
and I haven't touched it in months because I'm just like, nope, I'm doing Blazor.
Yeah, no, I mean, it really feels like it's changed a lot of things, and it really feels so much better than even MVC did.
Yeah.
It looks like SC Farmer was also looking to relearn Angular.
Yeah, no, don't bother.
I will say though, like, so I don't think WebAssembly supports sockets yet. So doing like any like video conferencing or chat things, which is part of like what I do, that's difficult in Blazor WebAssembly. You can still call the native JavaScript libraries, right? But it's more challenging from Blazor WebAssembly. So that's the only probably the only reason I would still use JavaScript.
Well,
so like WebRTC use cases.
Yeah, just build a WebRTC client for SignalR, and then you're good to go.
See, there we go. That's what I got to do. Because it's next.
SignalR is sockets, so it's got to be possible.
Yeah. Well, no. So hold on. Does remind me? Does Blazor WebAssembly use SignalR at all? I don't think so.
No, but like you said, I mean, you can throw in a SignalR hub and it's fully integrated, and
right.
And you only have to deal with the C#. So that's
yeah.
You know, if you can transmit the appropriate WebRTC data through SignalR, then it should be a pretty easy thing to set up.
Yeah, I don't think I'm going to mess with that though. I have to get work to pay me to do that. that's going to be a full bore effort.
Yeah, just tell them you need to make a spike, and they're just going to have to support you for a few months. Code crumbles. Yes, you can use JavaScript in Blazor. It's
you
not.
Can. Yes.
That is the one place where Blazor is not the best API. Really, all you can do is like invoke an asynchronous call to the JavaScript, and then wait for whatever response you get back.
What I would really like to see in Blazor is like a some way of marshalling objects between native JavaScript and Blazor, because it doesn't feel like it's quite there yet.
No, it's very aggravating when you create like an element ref to something like to a canvas, and then you try to pass that element ref through a JavaScript method so that your JavaScript can go, oh, that's the element you want me to use, and it just gets like an integer 1, and it's like, oh, what do I do with this?
Yeah, and if you kind of want to reference any variables in JavaScript, you need to have them kind of all at the window level too.
Yeah.
So
yeah,
it's problematic.
I use an IFI, the immediately invoked function expression, and I namespace my JavaScript, so it'll be like I'm working on a monogame reimplementation in Blazor right now, so it'd be like Blazor game dot, so window.blazor game dot whatever would be my JavaScript path.
Gotcha. That makes sense. So is there, hold on, I'm trying, I don't get to use Zoom that much. I'm trying to see if there's a way that I can not have the little thumbnail video over here. I'm looking at the Twitch stream.
Well, yeah, you could. If you go to view,
you can minimize the thumbnail completely.
Right, but like there's like a little delay on the Twitch stream.
Yeah.
So I can't really like
slight delay.
Yeah. These are 21st century, or these are 2020 problems.
See, what I want is I want a chat application like Zoom or Teams or whatever, where Vonage, I don't know, where it has individual windows for the cameras, and I can make them full screen, I can make them part screen, I can do whatever I want to with the cameras on their own in their own window, and then also have a window for any screen sharing that's going on. Because with Zoom, every single time somebody logs in, logs off, shares their screen, whatever, it changes all the positions of all the cameras. And the streaming software, it doesn't know where the cameras are. It can't like attach to them. So I've basically highlighted sections of my screen where a camera should be, which is why like when you stop sharing the video, it screwed up the layout on the stream. But if the cameras were their own window, then I could say, Zoom, this camera is that window, and then I don't have to mess with that anymore. But none of the applications that I've looked at do that. They all like, oh no, we have a window, and all the cameras are in that window. But I want each camera to have its own window.
So I'm not much in the streaming game, but I know a lot of my colleagues at Vonage are. So I wonder if that's something that they've encountered. Like, this is probably only like the 4th or 5th time I've been on actually a stream before, and they've always been dealt by someone else has always dealt with the technical difficulties. So it is interesting to listen to problems that people encounter with them.
Yeah, it's not too bad once you get everything set up, but like the slightest thing, like if you lost internet all of a sudden,
right,
the layout for the stream is just done. Like I can't do anything with it.
I think we use something called StreamYard.
Yes, I've seen that. I think the .NET stand-up uses that right now, and that's pretty cool.
Yeah.
But then it also has its own limitations. Like everything has to be within StreamYard. Like you can't. less configurable for some things.
Yeah, I got you.
All right, chat. Any more questions for Steve? We can continue hanging out and shooting the breeze, talking about computer vision, talking about Blazor, talking about technology, talking about streaming.
So wait, now if someone doesn't do a drop for a while, it just goes away?
Yeah, it just times out and goes away.
Gotcha.
It resets
And now
every so often.
Is this like a Halloween themed one, or is this just
it's
a
a Halloween
standard drop?
one. Yeah.
Nice.
I can there's a red pool that you can drop into, a blue pool that you can drop into, a pile of leaves that you can drop into, the cauldron. There might be some other stuff. And they've got other games too. There's some that look like they might actually require, control, like interaction. I have no idea how that works though.
Nice.
We started simple with drop because it's just drop.
Yeah, like it is cool to see like people do all sorts of neat things. Like John, you were talking about Michael Jolly before, who's one of my colleagues at Vonage. He builds all sorts of neat stuff on that stream. He has like I think he has like some kind of puppet that you can manipulate in the background on his stream usually, and he has you can change like the colors in his VS Code instance using the commands in the chat.
Yeah, I've been keeping live streamers on during the day, keeping me company during work hours. There's one gentleman that has one of the little robots that you can do voice commands to, and you can send chat commands to it, and it'll respond and say things. There's another gentleman that's doing some Dungeons and Dragons themed game development that you can play through chat and roll dice and do all kinds of crazy stuff.
Nice.
Yeah, I need to watch that one. Or, not watch that one while I work on stuff that I'm supposed to be working on. Yeah.
No comment. There's a chicken one that I watch. I think it's called Our Chicken Life or something like that. I only do it very infrequently though. I don't watch a lot of Twitch, unfortunately. Or maybe fortunately, I don't know.
I try to concentrate during the day. It's not always easy.
No.
Yeah, I've gotten used to a certain amount of noise, so it's actually helpful.
Yeah. Have either of you participated in Hacktoberfest at all this year? No. Well, we're actually Vonage is actually sponsoring Hacktoberfest, so we've been handling the inbound PRs for it. It's been actually pretty interesting. It's been a lot of fun.
Nice.
I would love to do stuff like that, but every time I commit myself to it, I just don't. So
I would like to pretty much all the repositories I work on are open source, so getting up to 4 PRs for me is like that's like a day's work.
Mm-hmm.
So it's not usually an issue for me to get there, but I would like to actually be able to contribute to some more major like .NET projects. I have one PR that I've submitted to actually Blazor, and that was a lot of fun, but I have to say, like, actually getting the whole runtime up and building was not pleasant.
I bet.
Like setting up your development environment was tough.
Oh, did you we've got a question in the chat. Have you built any APIs around the Emgu based projects?
No, I've not built any APIs surrounding it. And like I said, I have that sample that's actually posted in the resources.
Mm-hmm.
You'll see it if you look through some of the links that we dropped in here. You'll see it.
Okay. And it looks like we're starting to get some of the viewers dropping off and chat slowing down. So if there are no additional questions, then we can call it an evening, call it a night. Please do follow us, subscribe, do all the things. Join us next month. Here's a link to meet up again next month, where we have Michael Stark talking about Azure Bot Composer. And then in December, we've got Steve Smith talking about design pattern mastery. So with that, we will see you next month. Again, thanks, Steve, for joining us.
No problem. Have a good one.
Good night, everyone.
And we shall do the Twitch thing, and we will raid someone. Who shall we raid?
A person. Let's raid Callow Creation, shall we? All right. Good night, everybody. And there we go.
Cool.
All right. Now I need to